Hi, today we're going to continue using the quadratic formula and see how we can use this to benefit us in knowing what type of answers we will get. So if you look at example 1 and 2 and 3 and 4, each problem has been solved out using the quadratic formula with the work all shown out. And now we're going to just discuss what type of answers each example gave us. So with problem number 1, the final answer came out to be 6 and -2. And what type of numbers are 6 and -2? They're definitely real, not imaginary. 6 and -2 are nice numbers. They're rational numbers. And what we mean by equal or unequal is if the answers are equal, that means the same, or unequal, which means different, and they're different. Okay, you're going to hear these phrases today, so those are what they mean. Example 2. We got -1 plus radical 5 and -1 minus radical 5. Those answers are still real numbers, but they're definitely not nice numbers. They're irrational. And they are two different answers. That makes them unequal. Problem 3, we got two answers of 3 or 3. That really is actually one answer, and for that we would just say x is 3. So for this one, the answers are real numbers. They were nice numbers, they're rational numbers. And this time we did in fact get two of the same answers. That's what it means by when we say equal answers. And finally, on number 4, we have 1 plus 2i and 1 minus 2i. Those are imaginary because of the i's in them. And after we say that they're imaginary, we don't talk about irrational or rational. They are unequal, but they are going to be unequal each and every time. Okay, so those are the 4 different type of answers you can get. And if you go on to the next page, it says, look through each of the solutions of examples 1, 2, 3, and 4. What is the single most important part in the solutions that affected what kind of answers you got and how many answers you got? So if I go back and you look at the quadratic, or you look at the solutions, why did we get some answers like example 1 and 3 to be nice and the examples 2 and 4 not to be nice? The single most important part of the quadratic formula is the number that you get under the radical. If you get a nice perfect square number like example 1, you get 64, then that square root's going to go away and you will be left with definitely rational answers. If the stuff underneath the radical turns out to be not a perfect square, then that means that you know for a fact you'll have a radical left over, which is the irrational answers, and you'll have two different ones. If the number underneath the radical comes out to be a 0, well then your radical 0 is 0, and 6 plus 0 and 6 minus 0 are the same number. So therefore you get two of the same answers. And if the number underneath the radical is a negative number, then you know any negative number under the radical implies imaginary numbers. So that is the single most important part of the quadratic formula that's going to affect your final answer. So keeping that in mind, or let's write that. So the number under the radical of the quadratic formula is what affects what type of numbers you get, or what type of answers. And how many. Okay, so the number under the radical of the quadratic is what affects what type of answers you get and how many. So with problem 3 is, why is that important? It's a good idea beforehand to get an understanding of what type of answers you're going to have. So on problem 3A, I want to know what type of answers will I expect from that quadratic. All I need to know is what's the number that's going to be under the radical in the quadratic formula. Now that part of the quadratic formula is the b squared minus 4ac. That's the stuff under the radical in the quadratic formula. So if I fill this in, I can see what type of number I get. All right, so b is 2, c is 1, a is 1. So we get 2 squared minus 4 times 1 times 1. And that comes out to equal a 0 value. Well, if I know that underneath the radical, and you can do it off to the side, if that number is going to be a 0, I know that the radical is going to go away, and plus a 0 and minus a 0 still is the same number. So I know that I'm going to have real answers because the radical went away. I know they're going to be nice because the radical went away. And if you have a plus 0 and a minus 0, it's the same answer. So you know you're going to have two of the same answers. With b, a is 1, b is negative 4, c is negative 5. So again, if I want to know what type of answers I'm going to get, I just have to know this part. Okay, and that comes out to be 36. And again, if you want it, you can put it underneath the radical. The square root of 36 is nice. It is a real number. It is going to be nice, rational. And we're going to have two different answers because it's going to be a plus and minus 6, which are two different answers. C, a is 1, b is negative 6, and c is negative 5. Continuing to find that number under the radical because that'll tell me what type of answers I'm going to get. Okay, so this is going to be 56. Now, 56 under the radical is still a real number. This is not going to be a nice answer because radical 56 is not a perfect square, so it's going to be irrational. And we will get two different answers, so unequal. And then lastly, okay, you're going to get negative 8. And if you have a negative 8 under the radical, it's imaginary, and then we don't need to talk about those. All right, so that number underneath the radical is so special, we actually have a name for it. So when we go to our notes, first off, the roots. The roots are just a name for the answers to the quadratic equation. So when you hear the word roots, you can substitute the word answers in your head. Nature of the roots implies what type of answers are you going to have. So it's the classification, or i.e. the type of numbers the answers are. And lastly, the discriminant. This is another key vocab word. As I already told you, that number underneath the radical is so special, it has its name, and this is what it is. The discriminant is actually the name of the part under the radical in the quadratic formula. So the b squared minus 4ac part under the radical of the quadratic formula has the name discriminant. All right, so we already talked about this. If the discriminant, the number under the radical, is a positive perfect square number, okay, it means that the the answers are going to be real. The perfect square number means the radical is going to go away, rational, and you're going to have two different unequal answers. All right, if the number underneath the radical is a positive non-perfect square number, that means that the radical will still stay there. So you'll have a real, but the answers will be irrational. And again, you'll still have two unequal answers. If the number underneath the radical is a 0, then you're definitely going to have real answers that are nice. And because it's a 0, you're going to have equal answers. And then lastly, if the number underneath the radical is a negative number, then that automatically means that you're going to have imaginary answers. Now we also have to understand graphically what's going on. So first off, I will do the problem, I'll do the problem graphically first. That way you can see what it looks like graphically before we begin doing the discriminant again. Okay, so if you recall, the roots of a quadratic are where they cross the x-axis. So for my example 1 problem, if I put in x squared minus 4x plus 9, if you notice, the graph of number 1 here is not crossing the x-axis at all. If it's not crossing the x-axis at all, this implies that the answers will not be real, and that is why we know automatically right now, if it doesn't cross the intersection at all, we know it's going to be an imaginary answer. So we know it's going to be that one. So that's what graphically that would look like. Now to do it the discriminant way again, we'll show you that it will come out to be that way in fact. So I can look at the graph, or I can try to do the discriminant, which is the b squared minus 4ac method. Okay, b is -4, c is 9, and a is 1. Filling in my values, you will get -20, and there's your negative discriminant, which also again implies imaginary. All right, so number 2, I can do it by the discriminant method, or I can take a look at the graph. So let's see what happens on number 2, just to pull in the graphs, because you are responsible to know how the graphs cross. Also, that they could give you 4 pictures, and you have to recognize what the roots are based on the graphs. Okay, taking a look at the graph of example 2. I can see that in fact the roots are crossing at the number 2. And they're crossing at the number 8. And on this particular 84, if you're having trouble because the pixels, you can't understand if they're actually in fact meeting, you could actually just go to the table and, oh, I'm sorry, it's -2. And you can just check that -2 is hitting 0, which it is, and then you can check 8 to make sure that was right. And that is in fact. So I can definitely tell that my answers are going to be -2 and 8. Those are real answers. They're rational answers, and they're 2 different answers. So if I go back to my graph here, if the graph crosses at 2 spots at rational numbers, then I know for a fact we're going to have real, rational, and unequal. Okay, taking away the graph now. I'll do it by the discriminant. Okay, so A is 1, B is -6, C is -16. Let's see, 36 and 64. Okay, that adds up to 100. So that means that that is a perfect square number, and therefore I know if it's a perfect square number that's positive, we're going to have real, rational, and unequal. Same answer again. All right, example 3. Let's see what happens with that. Okay, so for this graph, we could zoom in on it, but it is in fact hitting at one place. It's hitting right here, and that's the number -4. You can also zoom in on it if you're having difficulty seeing, but that is hitting one place. So if it's hitting one place on the graph and only the turning point, it's actually specifically the turning point. So if the turning point is hitting on the x-axis only, then I know for a fact that the answers are going to be real rational, and there are two of the same answers. That's why you see only the one turning point hit. Okay, and again, I'm going to do this now by the discriminant, so you can also see that. Okay, and if I get rid of this, all right, doing this by the discriminant, we will get and again, if you get a zero discriminant, we know it's real, rational, and equal. So keywords, if you get a zero discriminant, you're going to look for the word equal. That's your key. Or if you have the turning, the one spot on the graph, the turning point, that's going to be the word equal. If you get a positive non-perfect square number, the key word you're looking for is irrational in your choices. And then the positive perfect square number, you're going to look for the words rational and unequal. And the negative number, that's the imaginary and doesn't intersect at all. All right, so one last one. If I look at the graph of the last one, okay, if I look at the graph of the last one, what do I get? Okay, and this is the only one that graphically it's really not good to do. Just because it's hitting between two numbers does not mean that the answers are going to be irrational numbers. They could in fact be meeting at, let's see, 1, 2, 3, 4. They could be in fact meeting at -5.5, which would be a rational number. So on this case, the only time that if it's hitting at two decimal values, this is the only time where you cannot tell if it's the two spots at rational numbers or the two spots at irrationals, because decimals are still nice. It depends on what type of decimal it is. Is a terminating decimal, that would be rational number. If it's a non-terminating decimal, it would be irrational. So there is a way to do it off the graph, though. If you change it to a solving problem by putting your 0 in, making the 0 bold on the 84 calculator, and I graph it, I can now just do an intersection, second, trace, 5, and just all I need to do is find one of them. If one of them is nice, the other one's nice. If one of them is not nice, the other one's not nice. It's not going to be a mixture of one rational and one irrational. So I can see that that answer is not a nice answer. So that means I have two irrational answers. So again, this is the only time where the graphing technique wouldn't work as nicely. You will see examples 1, 2, and 3 with graphs, but this one would be really hard to give you as a graphing problem. So, oops. Okay, so let's see if I highlight now. This one is going to be my green answer. I'm looking for the word irrational, which is choice 2. And that's what this means on the graph. Okay, so this would be the only time that perhaps the discriminant method would be the better way to answer this. So A equals 1, B equals 5, C equals -2. And you're going to get 33. And that number underneath the radical, that's not a perfect square, and therefore you know it's going to be irrational answers. Okay, so using that to our advantage now. Example 5. The roots of a quadratic equation are real, rational, and unequal when the discriminant is what value? So this is also another typical question. You have to know about the discriminant. So you have to use the graphs and the discriminant values together. But in this case, we have to know real, rational, and unequal. Well, the key is rational and unequal. We're going to get those type of numbers if it has a perfect square underneath the radical. Now, we can go through each choice. If you get a negative under the radical, we know it's imaginary, so choice 4 would be imaginary. We know if we get a 0 underneath the radical that we have equal answers. That's your key. We know if it's not a perfect square number, then that's the key word irrational. So the perfect square number is what you need to have in order to get real, rational, and unequal. Number 6, which graph represents a quadratic function with a 0 discriminant? Well, a 0 discriminant means that you're going to have a plus or minus radical 0, which would be a plus or minus 0, which is the same thing. So this implies equal roots. And equal roots means 2 of the same. Choice 3 has imaginary roots because they're not even meeting. Choice 4 has 2 roots. Choice 1 has 2 roots. And choice 2 has 1 of the same. When the turning point hits the x-axis, that's when you have equal roots. Okay, and lastly, these are the toughest. We have to figure out what value of k would make choice A have real, rational, and equal roots, and then question B, imaginary roots. For the first one, when do we get real, rational, and equal roots? Equal implies that the discriminant equals 0. So for your problem, all I have to do is realize that if this value comes out to be 0, I will have equal roots. So I can figure out what k number is going to make this true. So filling in my letters, my A is 1, my B is k, and my C is 16. So I have k squared minus 4 times 1 times 16. I get k squared is, k squared minus 64 is 0. Add the 64 over. K squared is 64. That means that if k were equal to positive or negative 8, either answer, I would get equal roots for that particular quadratic. Okay, so when do we get imaginary? We get imaginary when the discriminant equals a negative number. All right, so how do we show a negative number? Well, negative numbers are numbers that are below 0. So to show a negative number, it would have to imply a number less than 0. We can't put an equal sign there because I have no idea which number I want it actually to equal. I just want it to equal any number below 0. So again, filling in my discriminant, Okay, so anytime we have an inequality, although you haven't been taught this, we are going to change it to an equal sign, solve it like we would an ordinary equal sign problem, put the numbers on the graph, and then do a test point. So let me test 0. Does 0 for k work? So it does in fact work, so that means it's any number between -8 and 8.